Welcome viewers once again to the lecture series on integral equation under NPTEL courses. In all preceding lectures, we have considered the two types of integral equations, that is Volterra integral equation and Fredholm integral equation, and we have considered different methods how to solve those kind of integral equation. This lecture is completely devoted to the discussion on singular integral equations. So, and these singular integral equations we will be considering two types of singular integrals. One is called just singular equations and others are weakly singular equations, and we will be considering two different methods how to solve those kind of integral equations. So, in this lecture we are going to discuss about singular integral equations. So, first of all we have a look at some singular integral equations. F x equal to lambda integral 0 to infinity k x comma s y s ds. This is a singular integral equation because upper limit is infinity. Another singular integral equation is y x equal to f x plus lambda integral minus infinity to plus infinity k of x comma s y s ds. So, in case here both upper limit and lower limit are both of them are infinite. So, this is again and singular integral equations. And another type of integral equation is given by that y x equal to f x plus lambda times integral a to x k x comma s y s ds, where this k x comma s, that is kernel, this becomes infinite at one or more points in the range of integration. So, these are actually three specific types of singular integral equations, and this type of integral equations we have to solve in order to find out solutions of different physical and other type of problems in different modeling approaches and in different problems of physics. Most of the time we encounter this type of singular integral equations, and there are several methods to find solution of this kind of integral equations, that is analytical solution as well as numerical solutions. Of course, within this lecture series we are not going to address about the numerical methods to solving this kind of singular integral equations. Now, before proceeding further, we just have a look to some particular examples which are this type of singular integral equations. One example is x equal to integral 0 to x y s divided by root over x minus s ds. Here at s equal to x, this kernel, that is 1 by root over x minus s, this becomes infinite. So, this is an example of an singular integral equation. Another well known singular integral equation, that is Abel's integral equation, is f x equal to integral 0 to x y s divided by x minus s whole to the power n ds, where 0 less than n less than 1. This is another example of integral equation. Now, we recall two important transforms, that is Laplace transform of a function is defined by y alpha, this is equal to integral 0 to infinity e to the power minus alpha s y s ds. This is the definition for Laplace transform of a function, and Fourier transform is defined by y omega is equal to integral minus infinity to plus infinity e to the power minus I omega s y s ds. Actually, these type of two transforms somehow related to the singular integral equations, because we can rewrite this type of transforms formula by this way, that we are considering transform of a function y and we are taking the Laplace transform. So, instead of alpha, here we can write f x equal to integral 0 to infinity e to the power minus x s y s ds. And clearly you can see this is an integral equation, which is a singular integral equation with kernel k x comma s is equal to e to the power minus x s. So, that means for this type of integral, that is integral 0 to infinity e to the power minus x s y s ds, suppose f x is known, then we are intended to find out the function y x. That means for which function y x, f x is going to be its Laplace transform, considering this x as the variable of the Laplace transform, then solution of this singular integral equation will serve the purpose. That means solution of this integral equation will gives us the answer that yes, if we take the Laplace transform of y x, then we will be having f x as its Laplace transform with the variable x. And similar result holds for this kind of Fourier transform, because instead of y omega, we can write here some g x equal to integral minus infinity to plus infinity e to the power minus I x s y s ds. So, considering the complex valued kernel, that is k x comma s equal to e to the power minus I x s, we can say that solution of that particular equation, that particular singular integral equation will gives us the answer that if we take the Fourier transform of the function y x, then we will be having f x as the result of the Fourier transform. Now, we can consider another important transform, that is sine transform, and in this case the function f x is defined by this formula f x equal to integral 0 to infinity sine of x s y s ds. So, clearly f x is nothing but the Fourier sine transform of y s. Now, with this particular example, we are going to discuss the fact that in case of singular integral equation for a particular eigenvalue, we can find an infinite set of linearly independent eigenfunctions. So, first of all, we assume that f x satisfies two properties. Number 1, f x is piecewise differentiable, for x greater than 0, and number 2, integral 0 to infinity modulus of f x dx, this exists. If these two conditions are satisfied, then we can use the inversion formula for Fourier sine transform. So, using the inversion formula for Fourier sine transform, we can find y x is equal to 2 by pi integral 0 to infinity sine of x s f s ds. Now, using the property, we can consider the integral equation which is given by y x, this is equal to lambda integral 0 to infinity sine of x s y s ds. So, clearly this is an singular integral equation. Now, if we choose f x that is equal to y x by lambda from above expression, then we can find y x by lambda, this is equal to integral 0 to infinity sine of x s y s ds. So, considering this f x equal to integral 0 to infinity sine of x s y s ds, and using the inversion formula just we have discussed, we can write that y x equal to 2 by pi integral 0 to infinity sine of x s f s ds, that is equal to 2 by pi integral 0 to infinity sine of x s y s by lambda ds. So, this is equal to 2 by lambda pi integral 0 to infinity sine of x s y s ds. So, we have started with the expression y x equal to lambda integral 0 to infinity sine of x s y s ds, and using the concept of Fourier sine transform of a function and its related inversion formula, we arrived at y x equal to 2 by lambda pi integral 0 to infinity sine of x s y s ds. So, of course, y x equal to 0, this is a trivial solution for both these equations, that is y x equal to lambda integral sine x s y s ds and y x equal to 2 by lambda pi integral 0 to infinity sine x s y s ds. Now, if we assume that y x not equal to 0, now we are assuming y x not equal to 0, and then we are intended to look at the possibility of existence of certain solutions, that is some non trivial solution of these equations, then these two expressions will be compatible if and only if lambda, this is equal to 2 by lambda pi, and which gives lambda equal to plus minus root over 2 by pi. So, these are two eigenvalues, and if we just start from y equal to lambda integral 0 to infinity sine x s y s ds, then we can prove using some other method that these are the eigenvalues. Now, here we are going to establish that lambda equal to plus minus root over 2 by pi is the eigenvalues for this particular problem. We can take help of an result from an integral, and that result is, we can use this result, that root over pi by 2 e to the power minus c x plus minus x by c square plus x square, that is equal to plus minus root over 2 by pi integral 0 to infinity sine of x s multiplied by root over pi by 2 e to the power minus c s e to the power minus c s plus minus s by c square plus s square ds. This is the expression. Now, if we write lambda 1 is equal to root over 2 by pi and y 1 x, this is equal to root over pi by 2 e to the power minus c x plus x by root over c square plus x square. So, that means, in the above expression we are considering only the plus sign, ignoring the minus sign. From above expressions we can write the result, that is y 1 x is equal to lambda 1 integral 0 to infinity sine of x s y 1 s ds. So, clearly this lambda 1 and y 1, they satisfies the equation y x equal to lambda integral 0 to infinity sine x s y s ds, and similarly for lambda 2 equal to minus root over 2 by pi and y 2 x, this is equal to root over pi by 2 e to the power minus c x minus x by c square plus x square. Again we can verify y 2 x, this is equal to lambda 2 integral 0 to infinity sine of x s y 2 s ds. So, that means for lambda 1 equal to root over 2 by pi, y 1 x equal to root over pi by 2 e to the power minus c x plus x by c square plus x square, these are the eigen values and eigen functions, and similarly for lambda 2 equal to minus root over 2 by pi, this y 2 x is the eigen function. Now, here c is actually arbitrary constant. So, whatever value of c, if you take c equal to 1, c equal to 2 and so on. So, any particular value of c will satisfy the result, that is y 1 x equal to lambda 1 integral 0 to infinity sin x s y 1 s ds. So, for each value of c you will be having a particular expression for y 1 x, and two unequal values of c we can prove that the functions root over pi by 2 e to the power minus c x plus x by c square plus x square, they are linearly independent to each other. So, ultimately we will be having for two characteristic values of lambda, that is root over 2 by pi and root over 2 by pi with pre-multiplied by minus 1, they are of infinite multiplicity, as each of them are corresponds to infinitely many linearly independent eigen functions, and this particular result in contrast with the non-singular Fredholm integral equation, where we have mentioned that if lambda is a multiple eigenvalue, then its multiplicity should be finite. So, this is one nice example, that is one part it serves an example of a singular integral equation, and again with help of this result we can verify that with a singular integral equation, if we are able to find out eigen values and eigen functions, then for a particular eigen value we can find infinitely many linearly independent eigen functions. Next, we consider Abel's problem. This Abel's problem, it is defined by f x equal to integral 0 to x y s root over x minus s ds. In first lecture we have discussed the origin of this particular problem. Now, we are going to solve this equation using the method of Laplace transform. You can recall for two functions f1x and f2x, convolution of these two functions is denoted by f1 star f2 and is defined by integral 0 to x f1 x minus s f2s ds. So, using this result, that is the concept of convolution of two functions, we can understand that right hand side of the Abel's problem, that is integral 0 to x y s divided by root over x minus s ds, this is nothing but the convolution of two functions, that is root over x and y x. So, therefore, considering the Laplace transform on the both sides of the given problem, we can write L of f x is equal to L of root over x times L of y x. Now, if we denote the Laplace transform of y x as y alpha, so we will be having this is equal to y alpha times gamma half divided by root over alpha. This gamma half by root over alpha is result of the Laplace transform of root over x, and therefore, we can write that f alpha is equal to y alpha times root over pi divided by root over alpha, which implies y alpha, this is equal to root over alpha divided by root over pi multiplied by f alpha. This is actually the expression for y alpha. Now, from here we can write this y alpha is equal to alpha divided by pi times root over pi divided by root over alpha times f alpha. Now, root over pi by root over alpha, this is actually Laplace transform of 1 by root over x, and therefore, we can write after taking the writing inverse Laplace transform formula or using the Laplace transform of the convolution of two functions, we can write that root over pi divided by root over alpha f alpha is actually equal to Laplace transform of integral 0 to x minus s whole to the power minus half times fs ds. This is the result, and therefore, y alpha, this is equal to alpha divided by pi times Laplace transform of integral 0 to x minus s whole to the power minus half fs ds. And if we denote this function as gx, that is gx equal to integral 0 to x fs divided by root over x minus s ds, then this given expression becomes y alpha is equal to alpha by pi L of gx. Now, we can use this result for Laplace transform, that L ddx of gx, this is equal to alpha times Laplace transform of gx. So, if we use this particular result, then we will be having y alpha, this is equal to 1 by pi Laplace transform of ddx of gx. Now, taking inverse Laplace transform of both sides, we can find solution of this integral equation as yx is equal to 1 by pi ddx of gx, and we have defined gx equal to integral 0 to x fs by root over x minus s ds. So, this is equal to 1 by pi ddx of integral 0 to x fs by root over x minus s ds. So, this is actually solution to the Abel's problem. Now, we just have a look towards a particular example, that how to solve this kind of problem. We can try to find out solution of this equation, that is pi by 2 into x square minus x is equal to integral 0 to pi y s divided by root over x minus s ds. So, clearly here f x equal to pi by 2 into x square minus x. So, first of all, we have to evaluate this integral, that is integral 0 to x f s divided by root over x minus s ds, and this is equal to pi by 2 integral 0 to x s square minus s divided by root over x minus s ds. Now, we can use the substitution s equal to x sin square theta. So, ds equal to 2x sin theta cos theta d theta, and from here we will be having pi by 2, limit will be integral 0 to pi by 2, because when s equal to 0, then theta equal to 0, and at s equal to x sin square theta is 1. So, therefore, theta equal to pi by 2, and therefore, we will be having x square sin to the power 4 theta minus x sin square theta divided by root over x sin theta, this multiplied with 2x sin theta cos theta d theta, and therefore, after rearranging these terms we can find this will be equal to pi times root over x, then x square integral 0 to pi by 2 sin to the power 5 theta d theta minus x integral 0 to pi by 2 sin cube theta d theta. In the previous step it will be cos theta. This one. Now, you can use the reduction formula, that is, if I n is equal to integral 0 to pi by 2 sin to the power n theta d theta, where n is a positive integer, this is equal to n minus 1 by n I n minus 2 with I 1 equal to 1 and I 0 equal to pi by 2. You can evaluate this kind of integral, and then substituting we can find pi root over x multiplied with x square into 4 by 5 into 2/3 into 1 minus x into 2/3 into 1. So, this expression results in pi times 8 by 15 x to the power 5 by 2 minus 2/3 x to the power 3 by 2. So, this is actually result of this integration, that is integral 0 to x f s by root over x minus s ds. Then required result to the given problem, that means solution of the given integral equation, is 1 by pi d dx of 8 pi by 15 x to the power 5 by 2 minus 2 pi by 3 x to the power 3 by 2, and after differentiation and cancelling this term pi, we can get the solution as 4 by 3 x to the power 3 by 2 minus x to the power half. So, this is equal to root over x times 4 by 3 x minus 1. So, this is the solution of the given singular integral equation. So, that means if you have this Abel's type singular integral equations, that is f x equal to integral 0 to infinity 0 to x f s by root over x minus s ds, its solution will be given by y x equal to 1 by pi d dx of integral 0 to x f s by root over x minus s ds. This is the solution. Now, existence of the solution in closed form depends upon the existence of the integral in the closed form, and sometimes we have to take help of some table of integrations in order to find out this integral that is involved with integral 0 to x f s by root over x minus s ds. Next, we consider the generalized Abel's integral equation. This generalized Abel integral equation is defined by f x equal to integral 0 to x y s divided by x minus s whole to the power n ds, where 0 less than n less than 1. The previous example, that is the Abel's integral equation what we have considered, that was for n equal to half. So, now we can write this expression as integral 0 to x x minus s whole to the power minus n times y s ds. I have written this expression only for the reason, again we are going to solve this problem using the Laplace transform method. So, taking Laplace transform on the both sides, we can find f alpha, that is equal to L of f x, and this is equal to Laplace transform of convolution of these two functions, that is x to the power minus n and y x, where n is ranging between 0 and 1, and then we can find the result as gamma 1 minus n divided by alpha to the power 1 minus n, this multiplied with y alpha. From here we can write y alpha, this is equal to alpha to the power 1 minus n divided by gamma 1 minus n multiplied with f alpha, and here again we are going to apply the same type of procedure in order to find out the solution of this particular problem. So, we can rewrite this expression as y alpha, this is equal to alpha divided by gamma n multiplied with gamma 1 minus n, then we will be having gamma n divided by alpha to the power n, this multiplied with f alpha, and this is equal to alpha by gamma n into gamma 1 minus n, then Laplace transform of integral 0 to x minus s whole to the power n minus 1 times f s ds, and then using the result that gamma n into gamma 1 minus n equal to pi divided by sin n pi, where 0 less than n less than 1, we can write y alpha, this is equal to sin n pi divided by pi times alpha into Laplace transform of integral 0 to x f s divided by x minus s whole to the power 1 minus n ds, and using the same procedure, that means L of g dot x is equal to alpha L of g x, we can write this is equal to sin of n pi divided by pi, then Laplace transform of d dx of integral 0 to x f s divided by x minus s whole to the power 1 minus n ds, and then taking the inverse Laplace transform on both sides and noting the fact that sin n pi by pi is a constant, we can find y x is equal to sin n pi divided by pi d dx of integral 0 to x f s divided by x minus s times 1 minus n ds. Now, we can simplify this result further by considering the integral involved with this result, that is y x equal to sin n pi by pi d dx of integral 0 to x f s by x minus s 1 minus n ds, keeping in mind that n is ranging between 0 and 1. So, considering this integral and using the Bypert's formula, we can write that integral 0 to x f s divided by x minus s whole to the power 1 minus n ds, this is equal to minus 1 by n x minus s to the power n f s limit 0 to x, then plus 1 by n integral 0 to x x minus s to the power n times f dot s ds, and substituting the limit, we can find this is equal to x to the power n divided by n f 0 plus 1 by n integral 0 to x x minus s whole to the power n f dot s ds. Now, this integral, that is integral 0 to x x minus s whole to the power n f dot s ds, this is not an improper integral, and therefore, we can apply here Leibniz rule, and then we can write taking derivative on both side, that is d dx of integral 0 to x f s divided by x minus s whole to the power 1 minus n ds. This is equal to x to the power n minus 1 f 0 plus this n will cancel with this one, integral 0 to x f dot s divided by x minus s to the power 1 minus n, then ds, and this is actually equal to, we can write f 0 divided by x to the power 1 minus n plus integral 0 to x f dot s divided by x minus s whole to the power 1 minus n ds. And therefore, substituting this expression for d dx of integral f s by x minus s to the power 1 minus n dx into the previous step, we can find solution to the given problem is y x is equal to sin n pi divided by pi times f 0 divided by x to the power 1 minus n plus integral 0 to x f dot s divided by x minus s whole to the power 1 minus n ds. This is the result. Now, before concluding this type of singular integral equation, here I will be considering one more example where we can show that directly we will not be able to find out solution to this problem into the closed format, but we can find out an approximate solution of the given problem, and this approximation is depending upon the assumption that x is very small, x is greater than 0, but x is very small. And the particular example is, let us try to solve this equation sin x is equal to integral 0 to x y s divided by root over x minus s ds. According to this last formula, we can write the solution will be sin x times sin pi by 2 divided by pi multiplied with 0 plus integral 0 to x cos s divided by root over x minus s ds. In the given problem, f x equal to sin x, f 0 equal to 0, f dot x is cosine x. So, therefore, solution comes out to be 1 by pi integral 0 to x cosine s divided by root over x minus s ds. Now, in this case, evaluation of this integral is little bit problematic, and we will not be able to find out solution of this integral into the closed format, but we can make an attempt to find an approximate solution where this cos x is approximated by 1. So, therefore, approximate solution y x is approximated to 1 by pi integral 0 to x ds by root over x minus s, and again using the same substitution s equal to x sin square theta, we can find this is equal to 1 by pi integral 0 to pi by 2 to x sin theta cos theta divided by root over x cos theta d theta. So, finally, we will be having this result 2 by pi root over x integral 0 to pi by 2 sin theta d theta. So, this is equal to 2 by pi root over x. So, that assuming x is very small up to the level when cos x can be approximated by 1, we can find that 2 by pi root over x is an approximate solution of this integral equation. So, if we assume that x is not that much small such that second power of x can be neglected. So, considering the smallness of x such that third and higher power of x can be neglected, we can approximate cos x by 1 minus x square by 2, and accordingly after evaluating the integral we can find a better approximation as a solution of this particular integral equation. Next we consider weakly singular Volterra integral equations. There are several analytical and numerical methods to solve this kind of equations, but you are already familiar with Adamian decomposition method. So, here we are considering Adamian like decomposition method to solve this weakly singular Volterra integral equation. This weakly singular Volterra integral equation is given by y x equal to f x plus lambda integral 0 to x y s divided by root over x minus s ds, where x belongs to 0 to n, where n is a finite positive number. And this problem we are actually considering for this particular kernel k x comma s is equal to 1 by root over x minus s. Of course, there are several other types of kernel and other type of weakly singular integral equation, but in this lecture series we are considering only one such example. And sufficient smoothness of f x actually implies the existence of unique solution for the given integral equation, imply existence of unique solution. I am not going to prove about this uniqueness and other things, and also not considering the convergence, but just describe how to solve this kind of equations. So, as usual we can assume y x equal to sigma n runnings from 0 to infinity y n x is the possible form of solution of this particular equation. And substituting this expression into the integral equation and assuming the interchangeability of the summation and the integral sign, we can find that sigma n runnings from 0 to infinity y n x, this is equal to f x plus lambda times integral 0 to x 1 by root over x minus s summation n runnings from 0 to infinity y n s ds. Then we can find out the successive iterates by equating y 0 x is equal to f x. We can find y 1 x is equal to lambda integral 0 to x y 0 s divided by root over x minus s ds, y 2 x is equal to lambda integral 0 to x y 1 s divided by root over x minus s ds, and so on. As we have assumed y 0 equal to f x, and depending upon the evaluation of this integral, theoretically this y 1 y 2 all these successive iterates are actually exist. So, once we have the expressions for y 0, y 1, y 2 and so on, then summing up this series actually gives the solution to the given problem. But one thing you have to keep in mind, that sometimes instead of considering y 0 equal to f x, we can decompose f x into two parts, say f 1 x plus f 2 x, and considering y0x equal to f1x will give us quickly what is going to be the solution, because a clever choice of y0x equal to f1x instead of it is exactly equal to fx, sometimes we can immediately find other iterates are exactly equal to 0, and we can illustrate this concept with help of an example. This example is, consider this equation yx is equal to root over x minus pi into x plus 2 integral 0 to x ys divided by root over x minus s ds. This is the integral equation. So, here f x is actually root over x minus pi x. Now, instead of considering y0 equal to root over x minus pi x, first we consider y0x, this is equal to root over x, and then actually we are considering here fx equal to f1x plus f2x. Then next iterate y1x will be equal to minus pi x plus 2 integral 0 to x root over s divided by root over x minus s ds. Now, for this particular problem x belongs to 0, 2, this is required for the convergence of this particular series. And now, if we evaluate this integral, then it will be minus pi x plus 2 integral 0 to pi by 2, similar as earlier, it will be root over x sin theta divided by root over x cos theta, this multiplied with 2 x sin theta cos theta d theta, and after evaluating this integral we will be having minus pi x plus 2 x integral 0 to pi by 2 1 minus cos 2 theta d theta. This is the integral, and after evaluating this integral we can find this is minus pi x plus we will be having pi x. The second integral is that is integral 0 to pi by 2 cos 2 theta d theta equal to 0. So, this is equal to 0. So, with the choice of y0x equal to root over x, we have arrived at y1x equal to 0, and therefore, clearly y2x, y3x and so on, all these quantities are exactly equal to 0, and therefore, solution to this particular problem is given by yx is equal to y0x, and that is equal to root over x. You can easily verify that yx equal to root over x is a solution to the given problem. Now, we consider one more example of this type. If we consider this equation yx, this is equal to 1 plus 2 root over x minus integral 0 to x ys divided by root over x minus s ds. Here x belongs to the interval 0 to 1. Then if we choose y0x, this is equal to 1 plus 2 root over x, then y1x will be equal to minus integral 0 to x 1 plus 2 root over s divided by root over x minus s ds. And just for your understanding, here I am dividing this integral into two parts, that is minus integral 0 to x ds divided by root over x minus s minus 2 integral 0 to x root over s divided by root over x minus s ds. And using the similar approach, if you solve this integral, then it will result in minus 2 into root over x minus pi x. So, assuming y0x equal to 1 plus 2 root over x, you are getting y1x equal to minus 2 root over x minus pi x. So, with this y1x, if you calculate y2x, then y2x will be equal to integral 0 to x 2 root over s plus pi s divided by root over x minus s ds. So, this is equal to 2 integral 0 to x root over s by root over x minus s ds plus pi integral 0 to x s by root over x minus s ds. Now, you can see in this y to x we are having 2 integral 0 to x root over s by root over x minus s ds, and in the expression for y1 x we had minus 2 integral 0 to x root over s divided by root over x minus s ds. So, that means if you consider this sum, then second term of y0 x will cancel with first term of y1 x, and second term of y1 x will cancel with second term of first term of y2 x, and so on. So, as n tends to infinity, after summing up and using the condition that x belongs to 0 to 1, so you can see some higher powers of x will come up if you calculate the further iterates for yn, and in this case this will be equal to pi x plus 4 pi by 3 times x to the power 3 by 2. So, this expression y0 x plus y1 x plus y2 x ultimately results in 1 plus 4 pi by 3 times x to the power 3 by 2, and this power of x will increase if you calculate further iterates, and other terms will cancel with each other, and ultimately as n tends to infinity you will be landed at the solution y x is equal to 1, and you can easily verify that 1 plus 2 root over x minus integral 0 to x ds divided by root over x minus s, this is equal to 1. So, that means y x equal to 1 is a solution. I have considered this example only for the reason, if you try to solve this equation by considering y0 x equal to 1, and if you do not take this 2 root over x within the consideration for y0 x, then you can find y1 x will be equal to 0 and all other iterates will be exactly equal to 0. So, that means for a clever choice of y x will give you the solution quickly. This depends upon the fact that whether the solution of the given problem will exist in a closed format or it contains a finite number of terms in x or not. If the actual solution does not exist in a closed format, and if it be a infinite series of x, then there is no way for this clever choice for y0. It only give you some idea that in case of closed form solution or solution having finite number of terms in x, sometimes this clever choice give you quickly the complete solution, because other iterates are comes out to be exactly equal to 0. So, today we can conclude at this particular point. We are not going to discuss anything more on the singular integral equation, but of course, there are lots of other theories and techniques dealing with the solution of singular integral equation. In the next lecture, we will be considering integral differential equation of both the type, that is Volterra integral equation as well as Fredholm integral equation type with integral differential approach. So, thank you for your attention.